Now we specialize to the case of a crystal where the electron density is periodic. Because the crystal has translational periodicity, the electron density can be expanded as a Fourier series in reciprocal lattice vectors as shown in this expression. Here the vectors capital G are reciprocal lattice vectors, and the coefficients n sub G are the Fourier coefficients of the electron density. Now let's substitute this expression into the intensity formula. Then we obtain the equation shown here, which is the heart of the reciprocal space description of diffraction. We now think carefully about the integral shown here. If G minus delta K is not equal to 0, then the phase oscillates across the crystal volume. Contributions from different parts of the crystal tend to cancel one another in this case, so the integral becomes very small, but is generally non-zero for a finite crystal volume. However, for an infinitely large crystal, the integral goes to 0. But if G equals delta K, then the exponential factor becomes 1 for every differential volume dV prime within the crystal, and the integral simply becomes the crystal volume V prime. That means the scattered contributions from the entire crystal add together coherently, and the measurable intensity is proportional to the square of the crystal volume multiplied by the Fourier series coefficient of a particular spatial frequency capital G that equals a given scattering vector delta K. Please note that in this expression, the summation runs over all reciprocal lattice vectors capital G. For a given scattering vector delta K, the diffraction intensity becomes appreciable only if delta K equals one of the reciprocal lattice vectors. So the diffraction intensity becomes large only when the scattering vector matches a reciprocal lattice vector. This is a remarkable result because it tells us that the reciprocal lattice is not just a mathematical construction. It directly determines the directions in which strong diffraction peaks appear. Now that we know that the diffraction intensity becomes large only when the scattering vector delta K equals a reciprocal lattice vector. So we have delta K equals capital G. This is one of the most important results in solid state physics, which is the Laue condition. Now consider elastic scattering from a periodic lattice. The Laue condition states delta K equals capital G, where delta K, the scattering vector, equals K prime minus K, the difference between the outgoing and incoming wave vectors. Rearranging terms, we obtain this expression. Let's now connect it to elastic scattering. For elastic scattering, the magnitudes of the scattered and incident wave vectors are equal. So we have K prime equals K. Then squaring both sides of this equation, expanding the left-hand side and using K prime equals K, we arrive at the last equation shown here. It states that the projection of the incident wave vector onto a reciprocal lattice vector G plus half of the squared magnitude of G must be equal to 0. This is another form of the diffraction condition for elastic scattering. We will rewrite this equation and elaborate it on the next page.